In Chapter 17, Electrical Potential, we are going to talk about electrical potential energy, voltages, equipotential lines, and capacitors, dielectrics, and energy stored in capacitors. So, two of the most familiar aspects of electricity are its energy and voltage. We know, for example, that great amounts of electrical energy can be stored in batteries. Energy can be transmitted cross-country through power lines and may jump from clouds to explode the sap of the trees in the form of a lightning bolt. In a similar manner, at molecular levels, ions cross cell membranes and transfer information. We also know how voltage is associated with electricity. Batteries are typically a few volts. The outlets in your home produce around 120 volts in US, and power lines can be as high as hundreds of thousands of volts. But energy and voltage are not same thing. A motorcycle battery, for example, is small and would not be very successful in replacing the much larger car battery. Yet each has the same voltage. So we will be working on the topics here, and we'll try to understand each of the differences. So electrical potential energy, these are the topics that are meant for this chapter, and we'll go one by one over these. So the first topic is the electrostatic or electrical potential energy and potential difference. The electrostatic force is conservative. Now, what do we mean by conservative? To apply conservation of energy, we need to define electrical potential energy. As we had talked about, electrical potential energy are in our mechanics course, where we talked about its defined electrical potential energy can be defined only for conservative forces. The work done by conservative force in moving an object from any two positions is independent of the path taken. The electrostatic force between any two charges from Coulomb's law we already know is K cube magnitude of charge 1 magnitude of charge 2 over r square. So we know the electrostatic force. It's a conservative force because the dependence on position is just like if we compare it to the gravitational force, that's mass 1, mass 2 over r square, which is also conservative force and does not depend on the path taken. In the previous chapters, we saw that in the mechanics course, we saw that change in potential energy is negative of the work done. The change in potential energy between any 2 points, for example, in our case here, A to B, equals the negative of the work done by conservative force on an object as it moves from point A to point B. So we can easily say change in potential energy is negative of the work done. In this case, we have a tiny positive charge, which is accelerated between this uniform electric field. We have a uniform electric field over here. And this is a positively charged plate and a negatively charged plate. In the middle, we have uniform electrical field. A positive charge, of course, will be attracted towards the negative electrode that is over there, and it's accelerated towards it. So some work is being done in moving the charge from A to B. And the work done, if we remember, is actually dot product of force. In this case, it's the electrostatic force. But if we remove the dot product and write this in the magnitude form, it's magnitude of force T, force F, and D, the distance of separation, and cosine of angle between them. But since the angle here is going to be 0 because the electrical force and the electrical field are in the same direction, so our magnitude of force is F into D, where cosine 0 is 1. But our electrical field, we learned in the past chapter that electrical field is given by force per unit charge. Or in other words, the electrical force can be written as Q times E. The magnitude of the electrical force can be written as Q times E. So therefore, our change in potential energy will be minus of the work done between A in moving a charge against will from A to B. So we put the negative sign here, and is going to be minus, instead of writing F, we can write Q times E and D. That's how we end up getting change in PE equivalent to minus QED. So the electrostatic force between any two charges is already known, and we know it is conservative, and we define the change in electrical potential in moving a charge from charge Q from point A to point B as minus QED. Again, E will be uniform over most of the region. I use the word most of the region because the electrical field is not same or uniform towards the edges, because then the uniformity decreases as we reach the edges, and the electrical field lines can actually change the direction at the pointy regions. So this equation of change in electrical potential energy is true for uniform field only. So the next topic we will have is about electrical potential. There's a difference between electrical potential energy and electrical potential difference. Electrical potential difference PE is minus QED. It is not the same as electrical potential. So electrical potential is defined as the potential energy per unit charge, analogous to the definition of electrical field. Just like we had electrical field as force per unit charge, electrical potential at any point, it is not the difference. It's, for example, VA will be electrical potential energy at A over Q. Electrical potential at B will be electrical potential energy at B divided by the charge. So there's a difference between change in potential energy versus electrical potential. By definition, electrical potential is defined as the potential energy per unit charge at that point. And then we go ahead and see the units of electrical potential, which is named after a scientist. We call this as volts. And it's 1 volt is actually based on, because potential energy is joules and charge is coulombs. So 1 volt will be 1 joule over 1 coulomb. So volts is a combination of, this is the SI unit, and it's a combination of joules and coulombs together. The potential difference, on the other hand, will be is measured by taking the difference between the point in the potential between 2 points. So for example, we have VBA. Using the same diagram, if we have to find the potential difference between the one end and the other end, we can, or maybe the final versus the initial, is VB minus VA. So we get VB minus VA, and if we substitute the change in potential energy, which is equivalent to minus WBA over Q. So the units for the electrical potential difference and electrical potential are still going to be joules per coulomb. Joules per coulomb is nothing but volts. So both electrical potential and electrical potential difference will have the units of volts that you are commonly used to using in your day-to-day life. As for potential difference, we always say 20 volts, 30 volts, or so on. When electrical force does positive work on a charge, the kinetic energy increases and the potential energy decreases. Like we already know, it's conservation of energy. The difference in potential energy, PE equal to B must be equal to PE, is given by PEB minus PEA. This is the difference in potential energy, and it is not the difference in potential. So this is energy. It only becomes difference in potential when you have VB is PE over B divided by Q. So that is VB, and minus PE over of A, potential energy at A divided by Q. So if you combine the two, you end up getting PEB minus PEA, which is the potential energy difference. That's the energy difference over charge Q. So we can see from our definition that positive plate is at a higher potential than a negative plate, because our positive plate is plus, which is always at a higher potential, and energy always flows from positive to negative. If you have to bring a positive charge back to the positive plate, work will need to be done against this force, which is actually impossible. So the unit volts is named after the scientist Alessandro Volta, who is best known for inventing the electrical battery. So it's best abbreviated as V. So wherever you have values, you put the unit as V for volts. It's very confusing because the symbol for potential is V, and the unit is also V, and the potential difference is delta V, because and then we can the unit is also volts as V. So you have to be very careful in remembering the units versus the symbols that are used. And if we wish to speak of the VA at some point to A, we must be aware that VA depends on the potential, where the potential is chosen to be zero. The zero of the electrical potential is given situation, in a given situation, can be chosen arbitrarily. And just as for potential energy, because only differences in potential energy can be measured. Often the ground or a conductor connecting directly to the earth or ground is taken as zero potential, and other potentials are given with respect to ground. Thus, a point where the voltage is 50 volt is one where the difference of potential between it and the ground is 50 volt. So in other cases, we will see we may choose the potential to be zero at infinite distances. As we go farther and farther away from the source charge, the potential will drop. So let's solve one of the problems from your textbook, as it's how much work does the electrical field do in moving a minus 7.7 microcoulomb charge from ground to a point whose potential is 65 volts higher. So we are basically asking to find out difference in potential. We are finding potential difference. And we have been given, we know the formula is change in potential energy over the charge. So you're finding how much work is done. And the work done, we can also write this as minus work done over Q, because change in potential energy is the same as work done. Our job is to find the work done. So work done will be equivalent to minus Q times delta V. So we keep the formula ready, and we have been provided with the voltage 65. So given to us is V, that is delta V, change in potential is plus 65 volts. And the charge Q is minus 7.7 microcoulombs. Make sure you convert 7.7 cross 10 raised by minus 6 coulombs. And then we go ahead and substitute the values. So this will be minus times minus 7.7 cross 10 raised by minus 6 coulombs. And the voltage, which is the potential difference, is 65 volts. Go ahead and put these numbers in your calculator and find out what the work done is. So we end up getting the work done as 5.0 cross 10 raised by minus 4 of joules. Next comes the analogy between the electrical potential energy and the electrical potential difference, which is very important to understand. So if we have a massive rock, to better understand electrical potential, let's compare this to the gravitational case when a rock falls from the top of a cliff. And the greater the height of a cliff, the more is the potential energy, as we know. And as we fall, the gravitational potential energy is going to reduce and kinetic energy increases. And we know towards the end, kinetic energy is max, and gravitational potential energy is significantly reduced and becomes zero once it touches the ground. In the same way, electrical energy, in this case, in our second diagram, we can see that two charges, plus Q and minus Q, plus 2Q. These are the two positive charges, right? And they are both at a higher potential, Q, which is a positive plate. And the potential difference, if we have to move them to VB, so source of electrical charge, this may be a little bit similar, but the major difference between the rock falling versus the electrical charge, because there are two different types of charges, plus Q, and we also have a negative charge. So the scenario is a little bit different. The electrical case is somewhat similar, but the potential energy change or work done can be done. It depends on both the potential difference and on the charge, whether it's a positive charge or a negative charge. The charge resembles the mass in the gravitational potential energy. And we have a significant difference. Electrical charges come in two types, plus and minus, whereas gravitational mass is always plus. So sources of electrical energy such as batteries and electrical generators are meant to maintain a potential difference. And the power outlet in your house, when you have 120 volts, is actually the potential difference. The actual amount of energy transformed by a device which runs the generators depends on how much charge flows, as well as the potential difference. For example, consider an automobile headlight connected to a 12-volt battery. The amount of energy transformed into light and thermal energy is proportional to how much charge is flowing, which in turn depends on how long the light is on. If over a given period of time 5 coulomb of charge flows through the light, the total energy transformed can be calculated. So for example, we have an electron TV tube. Let's take the electrons in TV tubes. So back in time, we used to have different types of televisions, which would have tubes instead of LED screens and all. Suppose in that tube, an electron is accelerated from rest. So electron is accelerated from rest. And through a potential difference, we can say let the potential difference be VB minus VA, or we can call it VBA, which is the potential difference, or you can call it change in potential difference, where change is the potential difference between A and B. And if I say that, let it be 5,000 volts, it's a pretty big number. So we can probably diagrammatically show it this way. And so this is my negative plate, and this is my positive plate, and the potential difference between the two can be assumed to be V delta V VA equivalent to 5,000 volts. And the electron from here, minus E, is getting pulled towards the positive plate, and this is a high voltage. If we remember, 5,000 volts is a pretty big number. So the electron will be accelerated at very high speed towards the positive plate. So charge on the electron is minus 1.6 cross 10 to the power of minus 19 coulombs. We know that. So if change in potential energy is going to be equivalent to, if we use the formula, potential difference between plate B and A, if we name this as B, and if we name this as A, is equivalent to change in potential energy over Q, we can find the change in potential energy. So that's going to be Q times VBA, which is minus times 1.6 cross 10 to the power of minus 19 coulombs and 5,000 volts. So the change in potential energy is therefore minus 8.0 cross 10 raised power minus 16 joules. So that's the potential energy change. What if I asked, I wanted to find the kinetic energy? Instead of finding the change in potential energy, what if I wanted to find out the change in kinetic energy? The potential energy lost by the electron, PE lost, is the gain by KE. So in other words, change in PE is minus change in KE. So the magnitude of this would still stay same. So your change in potential energy would be same, except it will be positive 8.0 cross 10 to the power of minus 16 joules. And similarly, if we are asked to find out the speed of these electrons, so if this electron now moved to the other plate, we can find out the electron Ke is 1 by 2 mv square, and because speed will be given by kinetic energy, and Ke is equivalent to 8.0 cross 10 to the power of minus 16 joules. The mass of the electron is 9.11 cross 10 to the power of minus 31 kgs. You can go ahead and find out the speed of the electrons by rearranging the terms here, where after rearranging, you'll have V is equivalent to square root of 2 cross 8.0 cross 10 to the power of minus 16 joules whole divided by m, and after m, instead of m, we can write 9.11 cross 10 raised by minus 31. It comes out to be equivalent to a tremendous amount of speed of the order of 4.2 cross 10 to the power of 7 meters per second. It's this fast that the electrons get attracted when they're in presence of high voltages.